Thank you for the invitation. It's very nice to be here. Yeah, so this is going to be a board talk, and it doesn't go so well with jet lag. So unfortunately, Brian is not here because he could help me. But anyway, just if I fall asleep, just wake me up, and feel free to help if you forget. So yeah, so this is. I'm going to talk about another approach to universality, and this is edge universality for the Dyson beta ensembles, which you have already you just heard about, and it's a different approach. The Dyson beta ensembles. Let me just write them down. So they're coming, of course, from random matrices, say real symmetric random matrices to which you put a weight which is exponential minus trace of V of M, where V is some potential. So this is the metric you put on, say, symmetric real matrices, and you could put them also in Hermitian matrices, and you would get some eigenvalue distribution in both cases, and you can write down what this eigenvalue distribution looks like. It looks like exponential of minus beta over 4, and let's see, so you have sum of V of lambda I, and then there is a Vandermonde, so the product of lambda I minus lambda j to the power beta I less than j. So this is the joint distribution of eigenvalues for this when beta equals 1 or beta equals 2, corresponding to the real and Hermitian case. But of course, you can define this more generally, and it makes sense. And the theorem, and we look at, there's some normalization constant, the theorem, what we look at, if we order these eigenvalues, and we have a following kind of theorem. Actually, let me put here some n, so that, which is the dimension, so that this is sort of looks as in the right order. What you should know in advance is that roughly, the Wigner semicircle law behavior, as you have seen from the previous talk, is following some measure which depends on V, right? It's the classical equilibrium measure. It satisfies some simple variational problem that you have seen, and so it has some upper edge E. And what the theorem says is that if you take the top eigenvalue, so the kth top eigenvalue lambda k, and let's say you subtract this from E, and you scale this by n to the 2/3, okay, and there's some constant that depends on V, then this converges to some lambda k, capital lambda k, where this process lambda 1, lambda 2, lambda k is some random process that does not depend on V. That's the point. So this is why we call it universality, and this is a jointly, of course, in law. And this is one way to state this theorem. So now this theorem has now many proofs. I can list 3. So first, there's ours, and for us, what we can have any beta, and what we need to have V is very restricted. So for us, V has to be a uniformly convex. So anyway, a polynomial with V second derivative greater than some positive constant. So this is our result. There is a version. There is a proof by Brigade, Erdős, and Yao, where beta has to be at least 1, but V can be essentially anything. I mean, it just has to have 4 derivatives. And then there's some decay conditions just so that the eigenvalues don't fly out to infinity, but that's all. And then there is also a newer proof. These are from June, and this is from November last year. So this is Beckerman, Figali, and Guillaume. And for them, I think beta can be anything, and the potential has to be, I don't know, a lot, 30, 38 or something like this, you know. But you know, it's still something very reasonable. So these are the proofs, and I'm going to talk about this one, partly because these are hard for me, but this is, let me say, so ours is, I would say, relatively simple, and this one is also relatively simple. This one is somehow very, very nice, but it's a combination of a lot of ideas that have been built up in universality, and there are lots of steps to get to them. And it's a beautiful proof to the degree that I understand. So let me just talk about ours. So basically, you know, these new proofs of universality, I'm not talking about the really old ones for beta equals 2 and beta equals 1, but the one for general beta and for IID random variables in the matrices. They you know, somehow always tend to come back to classical probability. So as opposed to studying formulas, they study something that comes from classical probability, which essentially means that you reduce it to somehow independent random variables. They have to come in, right? This is really not independent random variables. Okay? This is something much more complicated because there is this very strong interaction. So somehow you relate your problem to something which involves something independent or almost independence. I guess, you know, there is this method where you replace the independent random variables and you use estimates. That's one way. There is this method where you introduce dynamics into the problem, and the dynamics has these independent Brownian motions, and you can study the dynamics. And this is what we're going to do as well here, except we don't need to introduce new independent random variables. Instead, what we do is we do a change of coordinates in which the independent random variables or almost independent random variables will appear naturally. So let me talk about the change of coordinates. Okay, so change of coordinates. Okay, so for this change of coordinates, let's first assume that beta equals 1 or 2. Okay, and we have this matrix model. Okay, so we actually have a nice random matrix. So this is just first so that we understand better. You know that when you have a random matrix, there is or any matrix, there is a natural way to make it tridiagonal. So tridiagonalization. So it's the following. So let's take a vector. For us, it will be the first coordinate vector. And you look at this vector and apply the matrix to it repeatedly. Okay, and there's the dimension. So you have this, and you assume that you get a basis. So then this vector is called cyclic for A. And now you apply Gram-Schmidt to this. Okay, and then you get an orthonormal basis. And you write your matrix in this new basis. Okay, so write your matrix. Okay, so it's a standard simple exercise that when you do this, what you get is a Jacobi matrix. Okay, so it will be tridiagonal, symmetric, and if you did it right, the off-diagonal entries will be positive. Okay, so that's what the Jacobi matrix is. So it looks like this. And the BI are strictly positive. The AI can be anything. And of course, since you wrote your original matrix in this new coordinate system, well, in this new basis, the eigenvalues have not changed, right? So let's call this of T and A are the same. Now, of course, what you really care about for now is the eigenvalues under n of them. But this matrix has a little bit more information, right? This has 2n minus 1 pieces of data to describe it. So you may ask, what is the extra information that that this matrix contains in addition to the eigenvalues of the original matrix, right? And the answer to this is very simple, because you have fixed the first coordinate vector. The spectral measure at that coordinate vector has also not changed. Okay, so the spectral measure at E1 is just at a vector is just a sum of delta lambda I, but not with so it's not the eigenvalue distribution, but with weights that are am I doing this right? Yeah, with the inner product of the matrix with these. Sorry, I'm sleepy. So phi I E I. So this lambda I gets the corresponding eigenvector inner product with the first of coordinate vectors. So you get the first entry, and then you square that. Okay, so we call this Qi. Okay, so just because you have not changed the first coordinate, it's very easy to check that the spectral measure at this first coordinate vector of your original matrix and the new matrix are going to be the same. Okay, and as you see, so you have this data, which is lambda 1 up to lambda n, and Q1 up to Qn. Now notice that those eigenvectors, you can take them to be unit length, and in which case these things sum to 1, right? So there is this data, and then there is the data which is in that matrix, which is A1, AN, B1, Bn minus 1. So these are both data in essentially R to the 2n minus 1, right? And then this map that maps one to the other, it turns out to be 1 to 1. Okay, so this is a 1 to 1 map. It's a diffeomorphism. But it is highly nonlinear. Okay, so these things are really not so simple to get from one to the other. I mean, you have tricks, right? If you have a matrix like that, there are ways to compute its eigenvalues, but it's not completely trivial. So what is this map? Well, in some sense, it's an extremely simple map. I mean, it's a map from a tridiagonal matrix to its eigenvalues and the weights. On the other hand, it's a beginning of many theories. So one of them is orthogonal, not polynomial theory. Okay, so how does it connect to that? So you look at this spectral measure, okay, and you write the orthogonal polynomials with respect to this measure. Okay, this is a point mass. This is a measure that lives on n points, right? And then those satisfy a recursion. They always do, and then they realign. And the recursion coefficients are these MBs. So that's what these are. But it's also more connected to fancier things like the total lattice. So basically, if you have some fairly complicated but nice dynamics on these things, then it translates to linear dynamics on these things. And so generally, it generalizes to things like inverse spectral theory. And sort of more and more wider and wider generalizations of this correspondence go under the name of classical systems. So basically, you have here, you have here this tridiagonal matrix. You could instead think of this as some Dirac operator with some potential, and then there is a one-to-one correspondence between potentials and spectral measures here, and this one-to-one correspondence is the beginning of inverse spectral theory, and basically the most important theorem here was proved by de Brange in the 60s. I'm just mentioning this because I just learned from number theorists. Okay, I didn't know this. Is that de Brange, what he tries to do is to construct this operator for which the eigenvalues are the zeros of the zeta function, right? And of course he always it doesn't work, but this one I heard from important people like Makarov that this proof of his completing this equivalence is really beautiful and it's complete. And it's kind of interesting to know that what we do in a slightly different project, although we cannot relate the zeros of the Riemann zeta function to some kind of potential in this correspondent, what we can do is to relate the limiting eigenvalue process of a random unitary matrix to some potential. So it sort of fits into this picture, but that's sort of a story about the bulk. Of course, the limiting picture of this is also somehow fits into this story. Okay, so you have this transformation, and so let's just look at some example. Okay, so the simplest example is when v is x squared, right? So so then you can do this thing actually explicitly on the matrices. It's called this householder reflections, how you do this special tridiagonalization. I won't go into the details, but the main thing is that in this case, AI is going to be a normal with, let's see, I think there is a 1 over root beta, and it's going to be a normal with 0 and variance 1/2, and the BI is going to be a chi n minus I times beta, and also I think there's also 1 over root beta here. Okay, so this is in the case v equals x squared, then that's what you put into this tridiagonal matrix. So this is a theorem actually of Trotter. So this is 82. That if you have this tridiagonal matrix for beta equals 1 or 2, then its eigenvalues are the same as the eigenvalues of the GOE and the GOE. And for general beta, this was proved by Edelman and Dimitriou in 2000. This is general beta. So again, the theorem is that for v equals x squared, you take that tridiagonal matrix with this independent random entries, and its eigenvalues are going to be distributed according to this law. So as you see, this transformation, this change of coordinates, takes something which is fairly complicated to something which is extremely simple for probabilists, and it's very nice to analyze. Okay, so let me tell you what. So you have this tridiagonal matrix, right? Let me draw it like this. Okay, so because you can think of this as a graph with weights, right? So you have this graph, because that's really right. It's an adjacency matrix of a graph with weights, and you have loops. So the AIs are sitting on the loops, and the BI are sitting on the edges. And really what this is a discrete random Schrödinger operator, right? Essentially, especially in this case, right? You have some, these chi's, if you look at them, what do they look like? Let me see if I got this right. Yeah, so these chi's, they look like, so chi m is approximately square root of m plus 1 over root 2 times a Gaussian. Okay, so or a normal, a standard normal. This is what these random variables look like, and so you can think of this as just the strength of the bonds here. So I put the big chi's up there. So bi is chi n minus I. Yeah, these chi's are decreasing. Right? So it's okay. So chi n minus I is square root of m minus pi. Okay, so basically you have something which has square root of I weight here on the bonds. And then you have some small perturbation. There's perturbation off both on the bonds and on the and on the off diagonals. So the nice thing about this already of this discrete Schrödinger operator is that it has a lot of structure. That is, questions that you ask about the random matrix are encoded in some nice and geometric way in this thing. For example, how localized an eigenvector is of this random Schrödinger operator, it corresponds to one single thing, which is where is the eigenvalue. Okay, so for top eigenvalues, so ones that are fixed distance from the edge, also from bottom ones, what happens? So maybe I should draw a picture here. So if you look at an interval which is of size n to the 1/3, this is where top eigenvalues live, or eigenvectors. Okay, so it's just in the very top of this matrix, and they already die out. And if you want bulk eigenvectors, they live on the entire length, but where you look in the bulk, actually there is a cutoff. If you look exactly in the middle, they go all the way. But if you look apart from the middle, then they stop at some point, and afterwards they just add. So what you can try to do, so you can, for example, try to read off from this operator what the top eigenvalue distribution is, and you can try to take a limit of this operator. Hopefully you get a limiting operator to get a limit of the eigenvalue distribution. And this is something that we have done. So with Ryder, Ramirez, in 2006, we did the edge in this case, and with Valko, we did the bulk. This was in, I don't know, 09 maybe. Yeah, I think it was on the slide up there. So you can take a limit of this operator, and actually in this case, actual limit of the operator. In the bulk, it's sort of a limit of some of the Sturm-Liouville problem associated to the operator, and you can get the limiting top and bulk eigenvalue distribution. And it's also good for defining, for example, Tracy-Widom distributions for general beta. So that's how they were defined. Is that you take a limit, you get a limiting random Schrödinger operator, and the top eigenvalue of that, or bottom eigenvalue of that, is what we call Tracy-Widom distribution. So there is another thing, actually. If you want, so you read off the bulk by looking at things of order n. You read off the edge by looking at things of order n to the 1/3 on the top. But you can also read off simpler things. For example, there are two ways you can read off the Wigner semicircle law from this matrix. So let me tell you one of them. I really want to tell you both. So you should ask me in the questions about the other way, because I don't really have time. But let me tell you one of them. This is extremely simple. So you think of this graph, right? This is your graph, and what you know is that when you look at this vertex, then the spectral measure at this vertex is what? Well, I haven't quite told you yet, and I'm getting there. But first of all, the eigenvalues are just the eigenvalues of the matrix, and the weights, well, you can guess from the special beta case, they're going to be independent of the eigenvalues, because the eigenvectors were independent of the eigenvalues to begin with, and they're going to have a Dirichlet beta over 2 distribution. So that's what these weights are going to be. So what this tells you is that the spectral measure is pretty much just like the eigenvalue counting measure, okay? Because of law of large numbers, if you ask for any kind of large scale behavior, law of large numbers are going to hit in. Those Dirichlets are essentially independent apart from their sum, and any question you ask about this measure, this spectral measure here, is the same as if you asked a question about the eigenvalue distribution, okay? And so you just want to understand what is the limiting spectral measure at this vertex, right? So what do? You take a limit of the graph as seen from this vertex. Okay? And what's going to happen? Well, what do I mean by a limit of this graph, right? Well, the graph is not really changing. It's getting longer. I say the limit of this graph exists if for every r, the r neighborhood stabilizes after a while. Again, n goes to infinity. And also the labels converge. Okay, so let's say that's when I call the limit of this graph exists. So the rooted limit, or local limit, if you like. So the limit of this graph exists. It's very simple. And what's going to happen? Well, look at this. Well, these chi's grow like square root of n, so I'd better put a factor of 1 over square root of n here. Okay, so when I do that, I'm going to kill off all the rest of this behavior. The only thing that's left is this 1 over square root of n divided by square root of n. So near this vertex, the limit of this graph is just the half line. Okay. Is this clear? Right, this noise is going to die because I'm dividing by square root of m. The a's are of order 1. I'm dividing by square root of n. They're going to die. And of course, the fact that it's not square root of n, but a little bit less, well, that also is going to die, as seen from this vertex. So what do I get? In the limit, I get this half-line graph. And it's very simple to check from the method of moments, because the moments of the spectral measures are just these sum over paths, that the spectral measure at this root is going to converge. Okay, so what is the limit of the spectral measure? Well, it's the spectral measure of this graph here. Okay, and what is the spectral measure of this graph at the root? Well, unfortunately, there is here one computation. But if you know the fact that the semicircle law's moments are the Dicke paths, right? Which probably you all know, then it's obvious because the moments of this are what? Well, just paths that stay in the upper half plane and come back after k steps. So they're exactly the Dicke paths. Okay, so that's the proof, a quick proof with almost no computation of the semicircle law. And there is one that has even less computation, but I won't tell you that now. So what I'd like to talk about is how do you transform, of course, this measure here to this new coordinate system. Okay, let's see. So the right side is junk. It's like nobody really cares. The only time the right side matters if you're looking exactly at the middle of the spectrum. And then this last variable says, hi, I'm also needed. But that's, the bulk extends all the way here if you look exactly in the middle. If you look somewhere else, no, then it gets cut off. All right, so now how do we transfer the measure? Well, it's very simple. It's just a one-to-one transformation. So all you have to do is compute the Jacobian. Okay, and actually this has been done. So this is not so hard to do. There are many ways. Let me tell you one way, which is very ingenious and is due to Dimitriou and Edelman. The way is just to compute how the measure changes when you do this transformation the Trotter way, just for the beta equals 1 or 2 case. Okay, so you have some measure which you understand. You do the transformation. You do this Householder. You understand there's going to be some chi's. There's some new measure, and so you just from the ratio you can get the change of variables factor without computing. Now you can also do this directly by studying the orthogonal polynomials. The proof is 2 pages. It's in our paper, and so let me just tell you what the result is. Okay, so change of variables. So there are a few things that you have to know. So let me call you B1. Is just a product of b's. Okay, and let me call you B2. Introduce this product, which is k equals 1 to n minus 1 of bk to the n minus k. So it's this kind of strange descending powers. Okay, and let me denote q, the product of your q's. Okay, and delta is the Vandermonde. Okay. Okay, so these are the things I have to tell you, and then there's some identities, and these are also not so hard to prove. The first identity is that B2 is Q delta. So this is 1, and second is that the Jacobian is B1. Okay, so these are the two things that you have to know. Now, which way is B1? I don't know, so we'll see. It's one way or the other way. So okay, so what does this mean? It means that this is really nice because you see I have a delta here in this measure. So if I want to transform it to over there, I would really not like to see eigenvalues there anymore. All I would like to see is B's and A's. So this will, if I have a corresponding Q there as well, then I can transform it to a bunch of B's, and that's nice. Okay, and then this B1 is fine because I just get as a factor on the other side. So that's fine. Okay, so this means that this measure with some extra stuff. So I'm gonna put here Q to the beta. Okay, so what does this mean? It means that the eigenvalues are distributed like this, and the eigenvectors have the Dirichlet distribution, just like over there, right? With that Q. Maybe it should be beta over 2. So this measure, it transforms. Okay, I don't know. It should be beta over 2 anyway. Transforms to the following. Okay, so the measure that we get looks like this. So it's exp to the minus n trace of t of n. So what is this one? This just comes from this factor. It didn't change. Okay, I just moved that factor over. And then you have a product of k equals 1 to n of bk of beta times n minus k minus 1. Okay, so this beta times n minus k comes from this and this and this equality. Yeah. Oh no, sorry, it's v of t instead of t of m. Okay, and t is the tridiagonal matrix. Okay, so this factor just didn't change. This thing partly comes from this Q and Vandermonde, okay, and this minus 1 comes from the Jacobian. Okay, so that's that's what we get. And now what we do is sit down and look at this thing. So what is it? Yeah?
Your top measure times Q.
Uh-huh.
The bottom one.
Yes. So it's so when these are some weights on the Q's and the lambdas, right? And I do this change of coordinates, and I get weights on the A's and the B's.
Yeah, you want to study the top measure without the factor of Q.
No, I don't care about the Q. I just put them there. Okay. The Q's are the
Q is this Q, spectral measure?
Yeah, the Q's are the weights of the spectral measure. So in the classical beta case, this is the right thing. This is what the weights are on the spectral measure. Okay? And in the general beta case, I'm just going to define as this as the natural measure that I'm going to study. I get something on the A's and B's. If I don't care about the Q's, I just ignore the weights. I just study the eigenvalues of this. But putting in these weights helps me get a nice formula. If I put in some simple weights like 1 or some other things, then I get a massive formula that I won't study. I won't be able to study. Okay, so that's the point. There is a simple change of variables formula. Okay, so what does this thing look like? So first of all, when v is just x squared, we recover what we had over there, right? Because the trace of v of t is just the sum of the squares of the entries. So this thing is just a product, this measure, which means that the variables are independent. So nothing really to study. I mean, we already have that result. But what happens if v is quadratic? You don't really want it cubic because that can be uniformly convex. So you could take v to be some quadratic, and then what happens? Well, then instead of just when you expand this trace, right? You're going to have paths of length 4, and those paths of length 4 have to come back. Okay, so there will include variables. There will include variables that are at most distance 1 apart. Okay, so for example, B1 and B2 could be in a product over here. Okay, so what is a measure? What do you call a measure that has this property that you only have variables that are distance 1 apart? Actually, it's very simple. It's called a Markov process. Okay, that's what it is. It's a definition. It's one of the definitions of what a Markov process is. The joint distribution, you can write it as something where the variables that you have are distance 1 apart. So what you have to study in this case is not independent random variables, but a very strange Markov process. And in general, when the degree is not 4, you get, instead of a Markov process, you get a d over 2 minus 1 Markov process. What does this mean? It's just like the Markov property, except you have to keep, one way to say it is you have to keep track of d minus 1 over 2 random variables, and if you keep track of those, then it's Markov. Or another way to say it is if you fix d minus 1 over 2 guys, then what come before and what come after, they're independent. Okay, so that's what you want to study here. So before I get into that, I got myself a little bit out of order. So let me show you what I want to prove about this Markov process. So in this paper, Ryder, Ramirez, and Virag, we showed, right, that this, if you look at this what did we show? So you look at this operator, okay? You rescale your space according to this n to the 1/3. Okay, so you think of this as acting as an operator acting on a discrete line, which have been rescaled so that one step is 1 over n to the 1/3 length. Okay, so let's call this operator, I don't know, hn. So you look at this operator, you subtract it from the edge, which in this case, well, let's say that's, let's say that it's already rescaled. So maybe let's make the edge to be 2. So you take this operator and you blow it up by n to the 2/3. Okay, so this is an operator acting on R plus now. Okay, why is it R plus? Because it was acting on the discrete line, but I have embedded the discrete line into R plus, and this operator converges as n goes to infinity. You could say in distribution, or you could say there is a natural coupling of these operators such that they converge. Well, there is a coupling of these operators such that they converge almost surely as n goes to infinity to a continuum of a random Schrödinger operator. Okay, and what does this random Schrödinger operator look like? It's called the Stochastic Airy operator, and it looks like this. So its derivative, second derivative with respect to time with a -1, so that would be positive definite, plus a multiplication by t, plus a multiplication by 2 over root beta of b prime, which is the white noise, standard white noise. Okay, so that's what the operator is, and the convergence here is in the norm resolvent sense. Okay, so that basically means that the inverse converges in norm. And so automatically when you have such a thing, that gives you everything you want. Okay, so it gives you the eigenvectors converge, the eigenvalues, the eigenprojections converge, and the eigenvalues converge. So it's all as strong as you want it. So this is again acting on R plus a positive. So functions from R plus with positive, with f0 equal to 0. So with Dirichlet boundary conditions. So it's a little bit of an issue when you first look at it that you have to multiply here by a white noise, but it's actually very simple to define a domain for this operator, and it's a nice operator. But you'd better do it in some privacy. But nevertheless, if you have something which is not quite twice differentiable, right? Some function, you can plug it in here. You can multiply it by a white noise, but you don't get a function, but you get some distribution. You can multiply it by t, that's fine, and you can take a second derivative. You don't want it to be twice differentiable, because then this thing will, this is not going to be differentiable, and you're never going to get, never going to get the constant times your function. But if it's not twice differentiable, then these two bad things will cancel each other out. They can, and then you can get an eigenfunction. Right? You can get a solution of this applied to f equal to lambda f. And in fact, you can look at all solutions, and they're going to be exactly the eigenfunctions and the eigenvalues that you're looking for. So that's a simple way to define. You can also define. So if you call this h beta, you can also define a quadratic form, f h beta f, okay? Because just by integration by parts here, okay? When you integrate out the L2 norm, then you get some white noise, and you make that into a stochastic integral, in fact, you can make that into an almost sure integral, so an integral in the strong sense. So you can define this very precisely. So now I can state the result that we proved, in more completion, and the result that we proved that I'm talking about now is that the same thing. Okay, so the same thing holds. For, t or h, I guess I called it h there, but it doesn't matter. T for general V. Okay, and by general V I mean this polynomial. Okay, so you have the same kind of norm-resolvent convergence to the same stochastic operator. There are slight differences that I didn't point out here. So this edge will not necessarily be 2, because this measure doesn't necessarily go to that. And the scaling can be a little bit different. And also the embedding, they may have a constant there. It won't exactly be 1 over n to the 2/3, but maybe 3 over n to the 2/3 or something. Okay, but you have exactly the same result. Excuse me?
Do you need that V contain evolution term? The second derivative of V is
Yeah.
Can you see where you use it?
No. So anyway, but I'd like to first argue a little bit for this operator, because I like it very much. So this is, what this operator is, right, is a probabilistic description of in terms of, independent stuff, so not stuff that we like, of this limiting eigenvalue process, which is the Airy process. So we call this its eigenvalues are called the Airy, we call them the Airy beta process. Airy beta process. And it looks like, they are sort of on the positive real line. And there is the smallest one. We call that, I don't know, lambda 0, lambda 1, lambda 2, and so on. And because you have a probabilistic description, there are lots of questions that you like to ask about the Airy process and the trace-Vidon beta distribution that you can have a simple answer to using the tools that you like, probabilistic tools. So let me give you a simple example. So it's very easy to prove by bounding this B prime term, okay, that this H beta can be bounded above in the positive definite order, okay, so as a bilinear form by 1 plus epsilon times H infinity plus some C depending on epsilon, and the same below can be bounded below by 1 minus epsilon times H infinity, then some C depending on epsilon minus. Okay, so for every epsilon, yeah, these C's are random, but the epsilons are not. Maybe they can be the same. So And what is H infinity? H infinity is just the ordinary Airy operator, right? There's just no noise. It's gone. So what are the eigenvalues of the ordinary Airy operator? Well, if you remember, if you take this Airy AI function, at least Mathematica calls it AI, it looks like this. No, it doesn't look like this. It looks like it decays, and then here it oscillates more and more. Okay, so the eigenvectors of the but faster and faster. Whatever. So the eigenvectors of this, because it's a translation invariant thing, are just going to be this guy translated to in a way such that the boundary condition is satisfied. Right? So you're just going to move it to the zeros. And what this thing tells you is that you can bound the kth eigenvalue of this guy in terms of the kth eigenvalues of this guy. So what follows from that is that if you look at lambda I, okay, and divide it by let's call it z minus zi, which is the I0 of AI. Okay, so this I0, then this converges to 1, almost surely. Okay, so this is a kind of Wigner semicircle law type result for this infinite operator, and this is approximately they're precise asymptotics for this. So this is approximately constant times n to the 2/3, or I to the 2/3. So the ith eigenvalue is roughly like this in the random setting as well. And this thing is one line. I won't show you. It's very simple. Another thing that you can get is, the Tracy-Widom distribution has these funny tails. Like one side is exponential in x cubed, the other is exponential x to the 1.5. So you can prove that using this operator, and they're actually essentially you have to prove 4 inequalities, and 2 of them are really, really simple, because what you can do is you can just use the Rayleigh quotient formula and try test functions. And for the main order behavior, even the constant, you can just try test functions that are deterministic. So you can just plug in any function that you think will roughly be like the eigenvector. And what you get when you plug it into this formula, you get some. What do you get? You get a Gaussian, okay? Because what is it? You're integrating some fixed function against Weiss noise. So you get a Gaussian, and you have to do a tail estimate for a Gaussian, okay? And then you derive a tail estimate for your Tracy-Widom. So it's very, very down to earth. If you want to do the other bands, you have to do a little bit of Sturm-Liouville theory. So you have to do this. It's a little bit harder, but not much harder. Okay, so that was my pitch for the stochastic Airy operator. Now I just want to tell you how we show that this thing converges. So yeah, they become like the bulk. So we show, in fact, as a corollary of our proof for the bulk scaling. When we proved the bulk scaling here, we were very, very, we wanted to be extremely general. So we can look anywhere in the bulk. You can look extremely close to the edge. You can converge to the edge. You can get so close to the edge that you're almost at the edge. So it turns out that as a corollary, and it's proved there of that result, it follows that when you take this process and you shift it, then it converges to the sine kernel process. So that gives you something like that, I guess, fluctuations in some sense. But precise fluctuations of this you can also get, but not. This is probably not strong enough to give you something too precise. Okay, so how do you prove it? Prove this convergence. So let me just draw this again. This is my Markov chain. Okay, these are the A's and B's. So this is A1, B1, A2, B2. And so this is my Markov chain. Or d over 2 minus 1 Markov chain. So it's not really the simplest Markov chain you can think of, because it's not. So this trace of Vt, you can see that this is homogeneous. This is not going to depend on where you are, because you always see the same products of A's and B's when you expand this. But this thing, because of this power, is going to matter. So what it gives you is a magnetic field. Okay, so there is an outside magnetic field. So this is one thing that you have. It tells you where the B's like to be. Okay, it pushes them in a certain way. So this is one thing that you have. And the other thing that you have here is a boundary condition. It's just the fact that you don't start from equilibrium, but you start from something which is and so these are the two things that you sort of have to deal with. And what you have to prove, what we wanted to prove, is the following thing. So in RRV, we established a bunch of conditions which would ensure that your tridiagonal matrix converges to something like a stochastic Airy operator. It could be more general, but let me just tell you what those conditions are. Actually, I'm just going to tell you the first one. So the first one is the following. So if you take the sum of I equals 1 to t times n, okay, t times n to the 1/3. Okay, so you take these partial sums of your AIs plus maybe 2, or the edge minus the BIs twice, I think, something like this. Maybe minus AIs plus twice the edge minus BIs. So you sum these. Okay, these are sort of these are not the big part of the AIs which we saw the limit of. These are just I already subtracted the big part, right? This edge was the big part there, and up to n to the 1/3, all you see is an edge plus some small order correction. You don't see that it's a square root. So when you do this as a process, okay, so t greater than or equal to 0, this has to converge to what? Well, to whatever is the potential here. So it's going to have to converge to t squared over 2 plus 2 over root beta times b. Okay, and this has to be uniformly on compacts. Okay, so the condition was, fortunately, not like something nasty thing like white noise have to converge, but the integral version has to converge. Okay, so this was one condition, and then the other condition was some kind of tightness. I'm not going to go into that, but it essentially tells you that the potential sort of controlled by this t for large values, and the b actually doesn't matter so much when you go out of this range. So this is the condition that we essentially have to check. So you have to check that this Markov chain, when you integrate its values in this sense. Oh, I forgot to put the scaling. Yes, I think it's n to the 2/3 is the scaling here. Okay, so this converges to this as a process. So this Markov chain, when you integrate its values this way, is going to converge to t press Brownian motion. So that's what we try to prove. But we got very quickly disappointed, because you see, this has to be something extremely precise. This A has to be, these are infinite. These are things that are of order perturbation order compared to the large term behavior. Right? Now remember, I gave you the proof. I gave you a proof of the law of the Wigner semicircle law. Right? What was that proof? This proof said that this operator, when I look near the edge, it converges to just the adjacency matrix of the half line. So that is something is not going to happen for general V. Because for general V, the Wigner semicircle law is not a semicircle, it's this other blob. So the thing that it will converge to is something which encodes the law. Okay? It's not going to be, whose spectral measure at the root is not going to be what you expect. So even the first order behavior for V is wrong. Okay? So you have to somehow get rid of this first order behavior and do something. Did I make myself clear here? Right, so you need, and actually what is this? So what you get as a limit is just what you get as a limit is exactly the correlation, the recursion coefficients for the orthogonal polynomial with respect to this measure, which is e to the minus vx. So that's exactly what you get on these weights here. So it's something classical. So why is this? And when you look at the Markov chain, you know that this behavior is going to happen. You look at the Markov chain and see where does it come from the Markov chain. And the answer is very simple. It comes from the boundary conditions. Okay, it comes from the fact that you don't start this Markov chain at zero in equilibrium, but you start it in something else. So fortunately, you have two things that come to your rescue. Okay, so what you do is, one is that the Markov chain mixes exponentially. Okay, so this is something that we use all the time. It's behind the ideas is we don't prove it explicitly like this, but this is the main thing. So in logarithmic number of steps, this boundary condition will disappear, and the Markov chain goes into this local equilibrium. The equilibrium is not the same everywhere, but if you look at constant times n, then it's going to be something which corresponds to the magnetic field that is there. So at every stage there is some local equilibrium, and it will be there. So this helps very much. So what we do is we take this tridiagonal matrix and cut off a logarithmic size in the beginning, and then the rest of that, actually this theorem will hold. Okay, and then we have to argue that cutting off this logarithmic chunk, which corresponds to the law of large numbers here, is not a problem. Well, you do it by two bounds. First of all, if you cut off this logarithmic chunk, you can only decrease the top eigenvalue. Okay, because you can plug in test functions that are zero there in the Rayleigh formula. And then on the other side, you have to show that this logarithmic chunk doesn't have a large eigenvalue, so it won't bother you, and then you have to put them together, and that's what we do. So this Markov chain mixes exponentially. This is one thing that helps us very much. Convexity, so we use Brass-Complete type stuff to show that things are concentrated or where they should be concentrated. We essentially look at this Markov chain and we compute what the equilibrium measure should be, and we just show by actually comparing densities that it's close to the equilibrium measure. So there is this quite amazing fact that this Markov chain is very closely Gaussian. It's almost Gaussian. So what do I mean by that? I can give you a precise statement. So if you look at a chunk of this Markov chain, okay, which is n to the 1/2 minus epsilon length, okay, and you look at this Gaussian approximation, okay, then the two, so it's really an n to the 1/2 minus epsilon dimensional random variable. Then the two get closer and closer as n goes to infinity in total variation. So they're extremely close to something Gaussian. And then you can analyze that Gaussian and show that it goes to this Brownian motion in the limit. So that's basically the chunk of the proof. Some technical details, but I can tell you over coffee.